So I'm going to talk about some of the technological innovations in CO2 capture using rotating packed beds. So I better start by introducing what process intensification is. I'll talk a little bit more in detail about what a rotating packed bed is, and then talk about scaling these things up from the lab, which is what we've been mainly involved in doing for the last 8 years. And then finally about a bit of technology, which Sakis alluded to, called the integrated stripper and reboiler, where we've actually brought the regeneration column and the reboiler together. What's process intensification? Well, it was started as a sort of area in a big chemical company in the UK called ICI, which obviously doesn't exist anymore. And it was always a technology about reducing the size of process equipment. And the big driver at that point was a cost driver, but also a safety driver. It wasn't long after a very serious incident in the UK, and people were very interested in making things more inherently safe. So ICI developed this rotating packed bed distillation system, which they trialed in 1981. ICI didn't invent rotating packed beds, and the first occurrence in the patent literature of rotating packed bed is 1913. So it's been invented many times over the years, but they were the first to really scale it up to an industrial process rather than being something in the patent literature. So, I mean, I got involved probably about 10 years after this development, and ICI were always interested in going after this separation, which is between propane and propene. And they were working on developing designs with multiple rotors. And then they got to the point where they realized that actually this thing was going to cost a lot more to run and wasn't going to improve their product quality. So it did reduce the size, did make it more safe, but ICI already knew how to operate the existing process safely. So it had to actually improve profitability. So in this context, process intensification always, yes, it reduces size, reduces capex, which is a really good thing. 20 to 40% reduction in capital costs, which you can see easily. This unit here sits on the ground. This unit has a big civil engineering cost associated with it. So you reduce the size, you reduce your cost, but you have to make sure you're not introducing any extra costs when you do that size reduction. Okay, so moving on, you've seen this already. This is a carbon capture process, solvent-based carbon capture process. And basically, if we're going to do intensified CO2 capture, we want to redesign that process to reduce capital and operating costs. We don't want to do just the capital, we want to get at the operating costs too. So I'm going to focus on the absorber and the solvent regenerator. I think James, when he talks from Carbon Clean's perspective, might well talk about some of the work they've done around intensifying all aspects of that process. So here's our absorber. We have the flue gas coming in at the base of a conventional pack tower and passing up through the packing and then through the water wash section. We have a lean amine coming in below the water wash and flowing countercurrently with the flue gas, and that's where the CO2 capture occurs. So when you want to turn that into a rotating packed bed, you've just got to be aware of the direction in which gravity is acting in that system. So it's down that column. When you start spinning it, the centrifugal acceleration is acting outwards, so the liquid flow has to follow the direction of the acceleration. And so we end up with this arrangement here. We've got packing, the liquid's coming in to the center and flowing out, and basically the centrifugal acceleration is causing it to flow radially outwards. We're bringing the gas in at the outside, and there's a pressure drop which you have to apply to push the gas in against that liquid flow, and it comes out of the center. So that's a rotating packed bed absorber. The diameter, or the radial depth of this packing is equivalent to the column height, and the length of this packing along the axis is equivalent to the column diameter. And if you want to know how long to make this. You do a flooding calculation at this inner radius because that's where the gas and the liquid velocities are the highest. And the reduction in packing volume that you get between this system and this system by doing rotation is about 50% due to the increase in flooding capacity, so you can reduce the column diameter, and about 50% due to the increase in mass transfer performance. So for the amine system, the packing volume reduction factor is around about 25. That's the high end of it. You know, the volume of this column is much smaller for a given separation. So that's been known since about 2007, that reduction in terms of intensification. There was a paper published based on work done in Newcastle in 2007, which showed that. So really, when I came back to this in 2011, so for a long time, there wasn't actually that much interest in using rotating pack beds for CO2 capture. But then in 2011, the interest started ramping up again. And so we built two test rigs. One's a small 300mm diameter gas absorption test rig where we can run with amines and work out the performance of the unit. And then a bigger 1 meter diameter hydraulic test rig where we can measure the pressure drop and we can look at flooding. And so we used those two bits of equipment to provide information that we could use to scale up these designs. So we wanted to go from lab scale to actually something that would capture 90% in an industrial setting. So that was the challenge. In terms of the packings that we use inside, you know, if you scale down your column, you're going to have to scale down your packing as well. And so we've been working over the years with two types of packing. This packing is basically expanding metal sheets. It wasn't made for the chemical industry. It was made for basically a plaster support. So you can actually see some poking through the bottom of that column over there. It's on the corner is a mesh which looks like that on either side. And so we got this basically from building supplies companies. We cut it into circular discs and stacked it, and it has some pretty good properties as a packing, besides being super cheap, which is a good thing for universities. You know, it had good properties. It had a good high voidage and a high surface area. So we were working with that for a while, and then we had a project called Rolling Cap, which is a precursor to this project, and we worked with Mons, and they developed this packing here, which is based on their vacuum distillation packing. So the base material is a very fine wire mesh that's crimped together into a structure like this. This is their A3750 packing, which has a measured surface area. We measured it using the hydroxide method of 830 meters squared per meter cubed and a voidage of 0.94. So a better performance. And when you actually test that in the lab on carbon capture, it's much better performing in terms of pressure drop and the rate of mass transfer than the expanded metal sheets. So, and this now is sort of dominant packing. That's a commercial packing now. If you talk to Mons, they say basically they have a business that makes RPB packing. Now that's a bit in advance of what I'm going to talk about next. So based on this packing material here, we worked on this project called Project Artemis, and we did this with Carbon Clean Solutions. And that was to basically build a unit that was going to capture 1 ton of CO2 per day from an industrial flue gas. And so we sized this unit here and built it. And this is the column behind, which Shakis has already shown. So this is in Glasgow. And yes, it is July 2020. And we were allowed to travel from Newcastle to Glasgow to work there because that site was open. And then it was followed eventually 2 years later by the regenerator, which is this integrated strip and reboiler. And we'll I'll talk about that in a bit more detail later. So these two units basically replace everything that you see on this structure there. And we designed the RPB absorber, so this unit, for 90% capture, and it was 1,100 millimeters in diameter, using the expanding metal mesh sheets. Okay, so we didn't have the money at the start of that project to actually use the Mons packing. The Mons packing would have been, well, was about 10 times more expensive than the mesh sheets. So we scaled up from the lab, and I'm just going to go through a list now of things that worked and didn't work in their scale up. So we calculated the inner diameter from this equation proposed by Agarwal, which is based on entrainment. So if you imagine the gas is coming out of the center of the rotor, and if you make the hole really small, the gas moves really quickly, and that will strip the liquid off the injection nozzles. So if you make the hole bigger, then you won't be stripping the liquid off the injection nozzles. That isn't the whole picture. So that's the reason why that didn't really work as an equation, because it's not just about the gas being stripped off the injection nozzles. When the liquid jets hit the packing, there's a certain amount of spray created when they hit the rotating packing. And so that is what causes the entrainment of liquid. So that didn't work super well. It was fine, it wasn't a problem. It was quite low, but it was still noticeable that some entrainment was occurring. The minimum rotational speed, that worked well. Basically, there are two flow regimes in a rotating packed bed. One is where you've got the packing rotating and the liquid's moving through it as rivulets. That's really associated with low speed. And then when you get to higher speeds, that changes into what we call spray and film flow, where the packing is more or less totally wetted by liquid, and you've got some drops flying through. And as long as you know what speeds you need to avoid rivulet flow, because rivulet flow is a low surface area flow, so you get poor mass transfer. As long as you know that, which we do from the work of Burns and Ramshaw, then you're okay. So that worked. The axial length from this correlation called the Lockett correlation, which is an RPB flooding correlation published back in the 90s. So a very old, well, relatively speaking, an old correlation. And that worked really well and continues to work really well. We've just literally tested the rotating packed beds for high record, which are much bigger, and it's still predicting the flooding point accurately. Packed bed outer radius from that formula there, it didn't work at all. I'm going to spend a little bit more time talking about what went wrong with that prediction. And then the pressure drop is based on the work we did on the 1 meter diameter. So we developed, well, it's not really a correlation. It's just we solved the equation of motion for the flow through the packing. And that predicts the pressure drop accurately. So the pressure drop predictions are good. And again, we've just tested the 2 meter diameter rotating packed beds for high record, and the pressure drop predictions are accurate. So that's still the case, even when we've gone to a much bigger system. So when we did our initial test with 30% MEA, we were getting between 59 and 66% capture, depending on the liquid to gas ratio. So this wasn't working, and I want to explore the reasons why. So the first one is a fluid flow reason. In a rotating packed bed, the entrance zone is where the liquid jet hits the packing and basically has to accelerate from having no rotational speed to the same speed to moving at the same speed as the bed. And you can see here, this is a CFD simulation of some packing. You can see the liquid bouncing off it. So that's some of your entrainment issue there. But basically this jet fragments and then sort of goes through the packing, eventually picking up speed. And we get very high rates of mass transfer in that area. Ooh. Oh, okay. And so you can actually split a rotating packed bed into 3 zones for mass transfer. You can have the entrance zone, where the liquid is accelerating from having no rotational velocity to moving at the same speed as the bed. You have the bulk zone, where the liquid and is moving at the same speed as the bed. And then you have the cavity zone where the liquid flies off from the edge of the rotating pat bed and hits the walls of the case and then runs down to the liquid outlet. So the evidence is, the experimental evidence is that the mass transfer zone, the mass transfer rate in the entrance zone is about 4 times the mass transfer rate in the bulk zone. So it's much higher. It could be higher than that. Some people say it's about 6 times as high, but it's significantly higher in that entrance zone than it is in this bulk zone here. And then in the cavity zone, the evidence is that the mass transfer rate in the cavity zone and the bulk zone are about the same, maybe a little bit higher. So in the cavity zone, the rate may be a little bit higher, but that's not fully understood yet as to what's going on there. And in our lab absorber, based on the best predictions as to how big this zone is, so this is very recent work, about a year ago, in terms of where that outer edge of that entrance zone is. It's about 9% of the volume of a 300 millimeter absorber. Okay. Now, the second part of the argument, of the reason why it didn't work, is the reactions that are going on with the MEA. So the process for absorbing the CO2 is that you get transfer of the gas from CO2 in the gas phase to the solution. Then the amine can react with the CO2 in solution to form a carbamate, and that's one route, or it can mineralize the CO2 via bicarbonate route. The fast transfer is fast. That amine reaction is fast, and those mineralization reactions are slower. They're not slow reactions, they're just slower than the carbamate reaction. And the amine loading is moles of CO2 per mole of amine. When we've got MEA, so this is for MEA, at low loadings, carbamate formation is favored, and we get very high rates of CO2 conversion into the carbamate. When that loading gets to 0.3, 0.4, we switch over to these slower reactions, and so we're not absorbing CO2 as quickly. And so what happened with our scaling up was that we basically used MEA in that 300 millimeter absorber with a very low loading. So we got this dominant carbamate formation. And then also that 300 millimeter absorber was influenced by that entrance zone. So we had, because we had a significant part of the packing that was operating at a much higher mass transfer rate compared to the rest, then we basically, we didn't take account of that. So basically, the Artemis absorber was undersized because we've measured data under the best possible conditions for CO2 absorption. That's the basic story. But it was an industrial project. So we had to try and make a success of it. And so fortunately about that time, TU Dortmund produced some data, and this is now measuring liquid holdup using gamma ray tomography in a rotating pat bed. So the red is around about 0.3, and then the yellow's going down towards 0 in terms of the volume fraction of liquid. And on the left-hand side, we've got some packing that has the porosity is the same all the way through. So the sort of hole sizes in the packing are the same all the way through. And so you can see that in this region, you've got high holdup, but then basically it drops away because the area for flow of gas and liquid is increasing as the radius increases, and so the holdup drops away. And they also did some measurements where they changed the porosity of the packing from 2.3 millimeter average pore size to 0.9, a number of radial bands. And you can see the effect of that is to basically increase the liquid holdup, which increases the liquid residence time in the packing. So you get an increase in how long the liquid's spending in the packing. From here, probably around about a second to maybe getting 2 seconds here. So not massive, but significant. And so we basically implemented that using packing that Mons supplied, a bed of variable porosity packing. And so we've not done anything about the mass transfer or anything like that. We've just given ourselves more residence time, because to do anything about the mass transfer, we'd have to increase the size of the rotor. We'd have to make a new rotor case, and that wasn't an option at that stage. And so for MEA, this is what happened. So we were able to get up to a maximum of around about 80% capture. So it's still not 90, but it's an improvement over where we were. And I think James will show you in the next slide that using their solvent in this system, they were able to get to 90% capture. So that, and the reason for that is because I think their solvent is faster when it has faster kinetics when the loading's higher. So really that's the story of scale up. Yeah, it's understanding why it failed so that we don't do the same thing again. That leads on to, so these have been designed with those lessons in mind. So these are the two absorbers that we're using for rolling cap, rotating cap bed absorbers. So on this one, this pipe here is the gas inlet, and it splits and goes into the sides of the rotating cap bed. The liquid's coming in down the center here. The gas is flowing out of this pipe. You can see it better on here. And the liquid comes out of these points here. They're two beds, 1.98 meters in diameter, 0.185 axial height. Got Mons variable porosity packing in, and there's also an amine intercooler between the RPBs to bring the temperature of the amine back down so that we get higher rates of mass transfer as well. So that's the absorber story. Much more detail on that because we spent more time with that. We go to the regenerator. In the regenerator, you've got a packed bed. You bring the rich loaded amine into the top. It goes down through the packing. At the bottom, you've got a reboiler that generates some steam, essentially from the lean amine. I mean, there's a little bit of amine in that stream, but it's mainly steam. And that steam basically heats up the rich amine, which comes in around about 110, heats up to 120. It also provides the energy to reverse the absorption reactions, and finally, it provides a little bit of steam to strip the CO2 away from the solvent. So if we can use an RPB to reduce the volume by a factor of 25, then why don't we supply the heat for the regeneration directly to the RPB rather than having a separate reboiler? So that's what we implemented. So this looks a bit complicated, so I'll just go through it. What we've got here is essentially the rotating packed bed. And this black line around it represents a physical barrier. It's actually encased in metal. Okay, so there's no liquid or vapor transfer across this black line. And instead it sits inside a pressure case, and we apply steam to it. We condense steam onto the outside of that rotating packed bed. And that provides the heat that we need to reverse the reaction, generate a bit of stripping steam, and to heat up the amine as well. So the rich solvent comes in, gets sprayed onto the rotating packed bed. We're generating vapor in there, particularly at the outside. We're generating some vapor that flows inwards. But we're also getting heat transfer through the walls of the column. It flows out. The regeneration generates a stream of vapor and water vapor and CO2 that goes that way. And we have to collect the liquid from the outside of the rotating packed bed using this scoop. Okay, so you can't let the liquid spray out because it would end up mixing with the steam. So you have to contain it and into a scoop chamber where we basically scoop it out to the middle, and it comes out and goes off that way. So that was quite well. That was quite a thing to design, quite a hard thing to manufacture, that scoop and scoop chamber that bring the liquid back from the outside. So the good thing about the integrated strip and reboiler is that size and capital cost occur because we've intensified the mass transfer, we intensify the heat transfer, and we integrate two units. And also we reduce energy consumption because we essentially just reduce any losses that are associated with having an external reboiler. So this is lab scale ISR. It's a bit hard to see it, it's sat in the back there. We've got basically a system where we feed liquid through to the ISR amine, we put steam onto the outside, and then we make vapor. These two are actually the condensers for the ISR in the middle there, and this heat exchanger at the bottom is the amine cooler. And basically, we're measuring the amount of steam we're consuming. We measure the flow of lean amine coming out, measure the flow of condensate, measure the flow of CO2 coming from that condenser, do all the titrations, and with all the temperature measurements, we can close the energy balance around that integrated stripper and reboiler. So for the heat transfer part first, we've actually measured, without doing CO2 release from the solvent, we've measured the rate of heat transfer and generated data for sensible heat transfer and evaporation. It's enhanced when there's vapor in there. So the rate of heat transfer to sensible heat transfer is not that much bigger than it would be in a normal heat exchanger, but when you get the vapor in there, it's very enhanced. The heat transfer characteristics are very similar to a plate heat exchanger. So this correlation here is actually a plate heat exchanger correlation that we've used straight for the RPB. And then the regeneration energy, it's this is well, the latest data we measured, which is earlier this year. And basically, we were preheating the feed to 90 degrees centigrade before it went in, and that was generating a lot more vapor than we needed. So we got these very high regeneration energy numbers. So when we didn't preheat the feed, then the regeneration energy drops down to being less than or around about what it should be for a packed column. But we haven't got that much data yet for this system, and we do need to keep measuring data to verify that, you know, there are more points like this. And certainly when we get onto some of the solvent that we're using for high record, we'd expect this to be significantly lower. Okay, so just conclusions. We scaled up from a lab scale RPB, and it's complicated by the entrance zone mainly. We showed that variable porosity packing was effective at increasing the rate of absorption just by increasing the residence time. We've integrated reboiler and regenerator columns successfully, and the regeneration energy is the same or lower than the packed column. All of this at a much lower capital cost than the conventional packed tower system. Okay, thank you for listening.